So far, we've talked about function definitions and examples of functions with definitions. So here in this session, we'll start by discussing different types of functions. Okay, so first of all, in order for an expression to be a function, what were the conditions that we came up to in the last session, at the end of last session? The conditions were that the first one was that each and every element of the domain must be mapped, right? That was the first condition. Each and every one of the elements in the domain, from the domain, must be mapped. The second condition was that every element from the domain should be mapped to exactly one element from the codomain. So if you remember the examples of the functions, so here, for example, this one was not a function. Why was this not a function from a to b to 0, ab to 0?
Because one is not in the codomain.
Element.
But in terms of the definition of the function, for this set and this set, why is this not a function?
B is not mapped.
Exactly.
I mean, A is not mapped. A is not mapped.
A is
sorry.
not mapped, sorry, yeah. A is not mapped, exactly. A is not mapped, all right? An element from the domain is not mapped. So this is not a function because of that. Here, clearly, B is not mapped, so not a function, because we need every element from the domain to be mapped, each and every one of them. Here, each and every one of the elements from the domain are mapped. A, B, both of them are mapped, yes, but this is still not a function. Why is that?
Because A is not, A is mapped twice. It should be mapped with once.
Yeah, A is mapped more than once, basically. Each of the elements from the domain can be mapped to exactly one element from the codomain. Whichever element it is, doesn't matter, but it can be mapped to exactly one element from the codomain. A here we can see is mapped to more than one element from the codomain, so not a function. Now, so these are the conditions in order for an expression to be a function. Okay. So on top of that, when can we say that a function is one-to-one? That is, what do we mean by one-to-one functions? By that we mean that for any function f which maps A to B, the set A to the set B, we say that for any two images from the codomain, if the images are equivalent to each other, the corresponding pre-images then have to be equivalent to each other as well. That is, for all elements in the domain, if you've got any pair, if there is a set of two elements from the domain where the result of the function applied to these elements are equivalent to each other, if you have this scenario, if this happens, if something like this happens, then it must mean that the elements themselves are equivalent to each other. If the images or the results are equivalent to each other, the corresponding pre-image or the corresponding element of the domain which gave you this result must be equivalent to each other as well. That is the condition for a function to be one-to-one. For all A1s and A2s present in the domain, the functions applied on them, if the result is equivalent, then the elements themselves which gave you the result should be equivalent as well. That is the condition for a function to be one-to-one. In other words, the contrapositive. What is the contrapositive of this statement, guys? This statement. What will be the contrapositive of this?
Miss A1 is not equals to A2. Then
That's it?
no,
A1
no,
is not.
the codomain will not be. They will not be the same.
Okay, A1 is not
I
equivalent.
understand, but I'm not able to interpret it properly, I guess.
Okay, anybody else? What will be the contrapositive of this expression? We have what here? An implication, a hypothesis which says that the result, if the result is equivalent, then the conclusion is that the elements of the domain which gave you the result must be equivalent as well. What is the contrapositive of this implication? Wow, nobody remembers what a contrapositive is.
Both of the equal to sun will be not equal to.
That's it. The contrapositive of this statement is that if the opposite of the conclusion is true, then the opposite of the hypothesis is true. Okay? Yes, instead of equal to, you'll have not equal to. Also, in the hypothesis, you'd have if A1 is not equivalent to E2. See? Very different. If A1 is not equivalent to E2, then it implies that the corresponding results are not equivalent either. Okay? So either one of these conditions, they are the same things. Or this implication is equivalent to this contrapositive. They're the same things. So, yeah, if you satisfy this condition, then the function is one-to-one. For example, here, okay, let's look at this function. Is this function one-to-one?
Yes.
In order to answer that question, first check if there are any results or any images which are equivalent to each other. Are there any images which are equivalent to each other?
No, miss.
No, they're not. No, they're not. No images which are equivalent to each other. Okay, so by default, this is not a one-to-one function at all. কোনো image নাই, এরকম কোনো image নাই. You don't have any pair of images at all which are equivalent to each other. So one-to-one তো হতেই পারবে না. Image কোনো equivalent আছে এরকমই নাই. So condition or hypothesis is false. The hypothesis of the condition is false. So by default, you don't have to satisfy the condition. Okay, or if you think about the contrapositive, where it said that if the pre-images are not equivalent to each other, then the images cannot be equivalent to each other either. If you think about that contrapositive, in that case, yeah, the pre-images. Let's look at the pre-images. 1 and 2. 1 and 2 are the pre-images, right? Are they equivalent to each other, guys?
No, miss.
No, they're not equivalent to each other. No, they're not equivalent to each other. And the condition is what? If they're not equivalent to each other, their images cannot be equivalent to each other either. Who's the image of 1? 3. What is the image of 2? 1. 1's image is 3, 2's image is 1. And as you can see, the images are not equivalent to each other either. So that condition is satisfied. The hypothesis, which is that if the pre-images are not equivalent to each other, which we see here, they are not indeed equivalent to each other, then the images cannot be equivalent either. As we can see, the images aren't equivalent. So both, in whichever way you phrase it, the condition for this being a one-to-one function, whichever way you phrase it, the condition is satisfied. So this is a one-to-one function. Now, is this a one-to-one function? That is the question. What do you guys think? Is this a one-to-one function? Yes? No?
No.
Yes, I don't think it's not a one-to-one function.
Probably not.
No.
Okay. All right. Most of you think it's not a one-to-one function. Fahim, I'm confused about your result. You don't think it's not a one-to-one function. So
No,
is that
it's
a
not.
negation?
It's not a one-to-one function.
So you don't think that, or you think that?
I think that it's not a one-to-one function.
Okay. I'm just messing with you. All right. So yeah. This is not a one-to-one function. You're correct. All of you are correct. This is not a one-to-one function. Why is that? Because here you see we've got two pre-images which are not equivalent to each other, 2 and 3. Are they equivalent to each other? No. But their result, is the result equivalent? Yes.
Yes.
The pre-images are not equivalent to each other, but the images are. Both of them map to the same image. So this is not a one-to-one function, yeah? This is not a one-to-one function. Yeah. All right then. So now that we've established what a one-to-one function is, let's do some more examples. Okay, let's consider the function x squared, the square function. Let's consider that from the set of integers to the set of integers. That is the domain and codomain. Both of them are going to be the set of integers. All right. Is this function going to be one-to-one or not? What do you guys think?
No, miss, it's not one-to-one.
Why is that?
Because if we consider 2 and minus 2, then we are going to have two answers. So it's not one-to-one.
We'll have two answers, two
No,
different.
No, it will be 4. Like if we consider minus 2 and 2 is going to be 4. So the contrapositive is false. So it's not a one-to-one function.
Okay, the contrapositive and the condition, whichever way you phrase it. See, remember again, the implication and contrapositive, both of them are equivalent to each other. It's the same statement rephrased. Okay, whichever you use, it's not going to be a one-to-one function. Okay, because just like you guys pointed out, minus 2 and 2 leads to the same result. That is, the image or the result is equivalent. However, we know what? That if the result is equivalent, it implies that the pre-image, that is the element from the domain which gave you the result, those should be equivalent as well. 4 and 4 equivalent, yes. But minus 2 and plus 2, they are not equivalent to each other. So even though the hypothesis is true, the conclusion is wrong. So not a one-to-one function. Even here, minus 2 and 2, not equivalent to each other. Yes, correct. However, the result, are they equivalent or not? Yes, they're equivalent. That is in this case, the hypothesis A1 not equal to A2, that is true. Minus 2 is not equivalent to 2. But the conclusion, the corresponding conclusion we should have had in order for this to be one-to-one was that the result should not be equivalent either. However, the result is indeed equivalent. And you can find many such examples for the square function if the domain is the set of integers and the codomain is also the set of integers. So it is not one-to-one, just like you guys pointed out. Very good. Okay, now,
Miss, but if the codomain was like the domain was positive integers, then it would have been a one-to-one function, right?
that was my question. You tell me. If the domain, instead of z, we had z plus here for the domain. For the domain, instead of z here, we had z plus, what would happen? That is the set of all positive integers. If we had the set of all positive integers to be the domain, what would happen?
Yes, miss.
One-to-one function.
Everybody thinks that this is going to be one-to-one in that case? Is that so?
We're not taking minus 2, so there is not like two elements. So how is that one-to-one?
Well, do you have to take minus 2 in order for this to be one-to-one?
Like we need to take two elements. We need
You
to
take any other
make
element.
sure that two elements are. Oh,
Take any other element. No, you don't have to make sure of anything. What do we understand by implication? A conditional. The conditional depends on the hypothesis. All right. If the hypothesis is true, then the conclusion has to be true. Only if this is true. Jodi eta true hai, then the conclusion has to be true. If this is true, then the conclusion has to be true. If this is not true, then by default, you don't have to worry about it. Okay. There you go. So if the domain was the set of all positive integers, in that case, you would never have a situation where the result is equivalent, but the pre-image are not equivalent. The elements of the domain that gave you the result are not equivalent. You will never get that scenario because it's all positive integers in the domain. That is, in other words, x will never be negative, right? X will never be negative, so you will never get that scenario where the result is the same, but the input is different. Is this clear to everybody now?
Yes, miss.
Okay, cool. All right. So let's just exactly prove that using the rules of logic. Okay. So here we have the same function, just like we've mapped right now. The domain now, C, is z plus. That is the set of all positive integers. So domain has changed from z to z plus, the set of all positive integers. We need to prove that this function is 1-to-1. All right. So using the rules of logic and the variables that we've seen so far, using those things, if you need to find out if f is 1-to-1 or not, let's assume that x is any element from the domain and y is some other element from the domain. Okay. So let's assume that x is one element from the domain, y is some other element from the domain. Both of these, both x and y come from the domain. Okay, two elements from the domain. Now, we'll start with the assumption. What was the assumption? fa1 is equal to fa2. That was our assumption. We'll start with this assumption. We'll start by assuming that the result of the function that we get from x and y are equivalent. Then, from that assumption, where do we have to get to? We have to get to this conclusion. If we can get to this conclusion from the assumption, then it's a 1-to-1 function. If not, then it's not. As simple as that. Now, based on our assumption, x and y from the domain, based on the assumption, we have fx is equal to fy. From here, we have to show that since these two are equivalent, since the result is equivalent, x and y are also equivalent to each other. Now, fx is equal to fy means what? X square is equivalent to y square, the function that is applied on x and y, x square, y square. So x square is equal to y square. If you bring y square to the other side, what do you have? X square minus y square. And how do we expand x square minus y square, guys?
X minus y, x plus y.
Exactly, x minus y multiplied with x plus y. Okay, elementary school. So here now, in this product, one is possible, the other one is impossible. Okay, x plus y, this one, is this going to be ever possible? X plus y is equal to 0. Is that possible?
No, miss.
No, it's not, because x plus y is equal to 0 gives you x equals minus y. And can x be negative? X and y are from where? From the domain. Can x be negative? What is the domain? The set of positive integers. Can x be negative?
No, miss.
No, x will never be negative. So x plus y is equal to 0 is an impossible scenario. So the only other condition that we have, that we're left out with, is x minus y is equal to 0. X minus y is equal to 0 gives us what? X is equal to y. X is equivalent to y. So we started from the assumption and we got to the conclusion x is equal to y, which satisfies our condition for a function to be 1-to-1. And there you go. That's how you show if a function is 1-to-1 or not. Is this clear to everybody?
Yes, miss.
Okay, now let's move on to the definition of an onto function then. Now, for any function f mapped from a to b, we say that this function is onto or surjective if basically every element from the codomain has been mapped as well. So far, what were the conditions for an expression to be a function? The first condition was that each and every element from the domain needs to be mapped. The second condition was that every element from the domain can be mapped to exactly one element from the codomain. However, if every element from the codomain is not mapped, that was not our concern, right? See, for example, here, is every element from the codomain, has every element from the codomain been mapped in this function?
No, miss.
No,
Which one is left out?
2.
2.
But this is still a function, yes?
Yes.
Yes, miss.
However, this is a function, yes, but this is not an onto function. This is not an onto function. Why? Because in an onto function, every element from the codomain has to be mapped as well. Basically, your codomain has to be equivalent to your range. This is an example of a function, but it's not a one-to-one. Sorry, this is not an onto function. This is not an onto function. This is a function, yes. Also, this is a one-to-one function. Yes, that is correct as well. A function which is one-to-one, but it is not onto. It is not onto, okay? This, for example, is a function that is not one-to-one. We established that previously. However, is this onto? Is this function onto? Yes, it is. Because if you look at the codomain, Has every element of the codomain been mapped here?
Yes.
Yes, miss.
Yes, it is. Yes, it has. So this is an onto function. What about this function? Is this one-to-one or onto? Which one?
Miss both.
Very good. This is both. This is an example of a function which is both one-to-one and onto. Okay. So basically, for an onto function, what you need is that your codomain has to have every one of its element mapped as well. Okay. So an onto function or a surjective function will be such a function where for all elements of the codomain, there is at least one element from the domain such that f is equal to p. Basically, every element of the codomain is mapped as well. Let's look at an example. So for the same square function, if the domain is the set of all integers and the codomain is the set of all positive integers, is this function going to be onto? What do you guys think?
Yes, ma'am.
Yes.
Yes, miss.
Okay, so 3 yeses. So everybody else, do they agree with this? Everybody agrees that it is going to be onto? Yes?
Yes, ma'am.
Yes, ma'am.
Miss, no, I think it's not.
Okay. Why do you think it's not onto then?
It says all integers, but if we like square root all integer, we're not gonna get.
It doesn't say all integers. It say it is mapped from the set of all integers to the set of all positive integers. The domain is the set of all integers and the codomain is the set of all positive integers.
Yes, miss.
Yeah. So go
So
ahead.
for example, if I square root 3, I'll not get an integer, right?
Yes, very good.
So it's not mapped. The codomain is not mapped, but it is in the range. So I cannot say it's an onto function.
So basically what you're saying is that even if the codomain is the set of all positive integers, even if it's the set of all positive integers, even there, the problem is that, so 3 is still a positive integer, yes?
Yes, miss.
However, so 3 is in the codomain, basically. 3 is in the codomain. However, would you ever get 3 as a result of this function? Would any integer from the domain give you 3 as a result once squared?
No, miss.
No, it would not. It would not. Think about 2 and 3 for x, for example. Set of all integers, right? So x is equal to 2 and x is equal to 3. Let's think about these two cases. 2 squares gives us 4 and 3 squares gives us 9. So we have 4 and 9 in the range, 4 and 9 in the result, yes?
Yes, miss.
But basically, what about the integers in between? Between 4 and 9, 5, 6, 7, 8. What about these 4 integers? These are positive integers. These are very much in the codomain. They are not ever going to be in the result because you will not find any integer. You will not find any integer in the domain which, when squared, will give you the result of 5, 6, 7, 8, or 3, the one that you gave. So, yeah, this function is not going to be onto. Is this clear with everyone? That
Yes.
this is not going to be
Yes.
onto. Okay. So don't be tricked, okay, just by looking at the domain and codomain. Think about it. Think before you give the answer, okay? So even if it's a set of positive integers, so what? Even for positive integers, what you have to see is that is there any integer out there whose square will give you all possible integers, all possible positive integers? No. Okay. Now, what if I change the domain and the codomain to the set of real numbers and the set of positive real numbers, respectively? That is, instead of z to z plus, what if we had r to r plus?
Miss, then it would have been onto function.
So, yeah, okay. What about the rest of you guys? Do you guys agree that it's going to be onto if we change the domain to R and the codomain to R plus?
Yes, ma'am.
Okay, Fahad agrees. What about the rest of you guys? Scared to give an answer? Okay, if you're scared here now, what will you do in the quiz? Okay, so yeah, think about it. Real to real plus, okay? So here, what was the problem originally? From Z to Z plus. From Z to Z plus, what was the problem? Problemটা কোথায় ছিল? Problemটা ছিল যে here, in the codomain, there might be some numbers which you will never get as a result once you square an integer, okay? That is, for example, here, 6, you will never get 6 as a result if you square an integer, any integer. The square of any integer will never lead you to 6. Now for R to R plus, however, it's real number. Fractions are allowed, right? Fractions are allowed. For all positive real numbers you have as a result, you will get another real number in the domain which gives you that result, right? Take 6, for example, okay? Now that it's real number, now that fractions are allowed, there must be a real number somewhere in the domain, the square of which would give you 6, yeah? So the previous problem that we had, the result, this result we will never get once you square an integer, that is not there anymore, okay? The square root of 6, whatever the value is, that value is the real number that will give you 6 as the result. So now, every element of the codomain now can be mapped to the domain in this function, okay? Is this clear to everybody? If we change the domain to the set of real numbers and the codomain to the set of all positive real numbers, then this function is onto. Okay, in that case, now tell me, if we changed the domain and codomain from the set of real number to the set of real numbers, that is just to change the codomain, that is. Instead of having R to R plus 1, sorry, instead of having R to R plus, what if we had R to R? That is, the domain is the set of real numbers and the codomain is also the set of real numbers. In that case, would it be onto?
No, miss.
Why not?
Yes, because they are negative real numbers.
Yes, exactly. Negative real numbers in the codomain, which you will never get as a result of the square function. So it's not going to be onto then.
Miss, I had a question.
Yeah, go ahead.
Previously you said to consider domain as R and codomain as R plus, right?
Yeah.
So like 0 is, if I take 0 for like domain, I don't get a positive real number because 0 is not positive, right?
Very good example. Yeah, but in that case, what is the, yeah, very good example, very good observation. Yeah, we missed out on that one. So R to R plus, okay? So what he's saying is that it's a legit point. 0 is a real number, indeed. However, is 0 a positive real number? No, it is not. So f of 0 would give you what? 0. But 0 is not there in the codomain at all, right? So the problem here, what you're saying is exactly correct, but the problem is not that the function is not going to be onto. Before that, think about it. Is this a function at all then, what you're saying in that case? R to R plus. Would it be a function even before you answer the question whether it's onto or not? For R to R
be a
plus,
function.
it won't be a function.
0 won't be mapped.
0 won't be mapped. Every element from the domain must be mapped. So 0 won't be mapped at all. So it won't be a function. So yeah, good example there.
Some is minus R to R plus all up there, right?
So yeah, you could say that all elements for which this function makes sense. Okay, so in that case, remember in calculus, we assume that when we say something like this, we assume that for those elements which make sense. So if you just mention that, in that case, you could say, but very good point. If that is not mentioned, in that case, R to R plus, in that case, this wouldn't be a function at all. Forget about onto, it wouldn't even be a function for R to R plus. Okay, so yeah, very good example there. So basically, it would be a function for all positive real numbers and negative real numbers in the domain except for 0, and the codomain being the set of all positive real numbers, but not otherwise. So yeah, good example, very good example. Yeah. So anybody else has any observation or any questions or anything?
Miss, I didn't exactly get what he said. Like 0 is not a real number.
0 is a real number. That is the problem. 0 is a real number, but it's not a positive real number. So if it's R to R plus, in that case, 0 is in the domain, right? R.
Yes.
If you have R here, 0 is in the domain, right?
Yes, miss.
But if you have R plus, that's the set of positive real numbers. 0 is not considered positive.
Yeah.
For the scope of our course, we will not consider 0 in the set of positive real numbers or positive integers for that matter. So 0 is not in the domain. So codomain, right? 0 is not in the codomain. Yeah?
Yes, miss.
Is that clear? Okay. Now, the condition in order for an expression to be a function is what? What are the conditions? Every single element from the domain has to be mapped. That is the first condition, right?
Yes,
Every single element from the domain has to be mapped. You just said that 0 is in the domain. But 0 square gives you what? 0.
Yes.
0, however, is not in the codomain. Remember this example? Yeah. Why was this not a function? Because A was not mapped. Why was A not mapped? Because A is not mapped to any element from the codomain. As long as A is not mapped to any element from the codomain, for our concerns, for this function, and for these two sets, A is not mapped at all. So think about that. 0 is in the domain, but if you square 0, you get 0, which is not in the codomain. Right side is just set touch. 0 nahi. So if you map 0 to 0, on the right side, 0 doesn't exist at all. So তুমি যে 0 কে 0 সাথে ম্যাপ করবা, রাইট সাইডে যে কোডোমেইনটা আছে ওখানে তো 0 এক্সিস্টই করে না, তুমি কি ম্যাপ করবা কিভাবে? Alright?
Yes, miss.
Do you get my point now?
Yes,
So yeah, that's why this is not a function at all, and if it's not a function, it sure as hell won't be an onto function. Okay? So yeah, you're correct. Okay. So let's move on to another example. Let's consider this example, m plus n. Okay, so for this example, for this function, basically, in the input, you will see that now we have something different. So far, we've dealt with functions where we applied the function on only a single variable. Okay, here we have two variables or multiple variables, basically, on which we're applying the function. In these cases, the way we represent the domain when we have multiple inputs or multiple variables or multiple pre-images, basically, is we represent them as Cartesian product of the sets. All right. So Z cross Z, which means that both of these variables come from the set of integers. Okay. So this is how we represent it. Because there are two variables, Z cross Z. If we had 3, we'd write Z cross Z cross Z. All right. That is all the variables come from the set of all positive integers. Okay. Now, the question, whether this function is one-to-one and whether this function is onto or not. So you will notice that mn is in an ordered pair. See, the function is applied actually to an ordered pair. Yeah, mn is an ordered pair. The function is applied to an ordered pair. Now, in case of ordered pair, what do we know? Even if the elements of two pairs are the same, is that enough to say that the two pairs are equivalent to each other? Remember ordered pair from set theory? So two pairs, in order for them to be equivalent, two ordered pairs, in order for them to be equivalent, they have to have the same elements in the same order, in the same exact positions. Remember? So now, in order to answer the question whether this function is one-to-one and whether this function is onto. For one-to-one, first of all, this is not one-to-one. Why is that? Look at the example that we use here. 0, 1, 1, 0. These two, are these two the same ordered pairs, guys? 0, 1 and 1, 0.
No, miss. No.
No, they're not equivalent. However, the result, if you apply 0, 1 here, 0 plus 1 gives you 1. If you apply 1, 0 here, 1 plus 0 gives you 1. The results are equivalent. So the result of these two elements is equivalent. But the elements themselves which give you the result, they're not equivalent to each other. So obviously this is not one-to-one. Same applies for any other example that you can find. Okay, you can find many such other examples for the given domain and codomain. Now, to answer whether this is onto or not, that part is interesting. So here you have mn and the function is m plus n. In order for this function to be onto, the condition is that it is possible to map every single codomain, elements of the codomain. It is possible to map every single element of the codomain. That is the condition we need to fulfill in order for this function to be onto. Now, every single element of the codomain. What is the codomain here? The set of all integers, all integers. Basically, you have to show that every possible integer you can get as a result of this function, the result of this function. It is possible to get every possible integer in the result of this function. You have to show that. Now, for any element, which is an integer, for any b, which is an integer, it is actually possible to show that 0b is equal to b. F of 0b is equal to b. If you fix m to 0, if you fix m to 0 and n to b, then you will be able to get b. So b can be any integer from the codomain. B can be any integer from the codomain. If you put that same integer here for the value of n, since the domain and the codomain, both of them are the set of all integers, that's fine. We can do something like that. So if you put b here for the value of n as well, then you will be able to get any possible integer from the codomain. Okay, just put b, set m is equal to 0 and n is equal to b. Okay, and that will give you the result. Whatever you want here, whichever integer from the codomain, whichever integer from the codomain you want in the result, just put that same integer for n, all right, in the function, and you will get the integer that you desired. So basically, it's possible to get all integers out there in the universe in the result. So this function is onto. Is everybody clear with this so far?
Miss.
Yeah.
I don't quite understand the Cartesian product. Like, how is this gonna be the domain? Like 0, b, is this a single element? Consider it like that.
0, b, yes, that's one element. Yes. Okay. 0, b is a single element. Yes.
Okay, miss.
So the reason this is onto doesn't have too much to do with that. The reason this is onto is mainly because, think about it. Onto origin, what do we need? We need to show that it's possible to get any integer in the result. Why do we need to show that? Because the codomain is the set of all integers. So since it's the set of all integers, every element of the codomain has to be mapped in order for this function to be onto. Yes? Yes, so you have to show that in the result it's possible to get any integer. Okay? এখন তুমি result যে ইন্টিজারটাই চাও, if you set n is equal to that integer, okay? If you set n is equal to, আমাদের কি করতে হবে? Basically, we have to show that প্রত্যেকটা integer এখানে result হিসেবে আসতে পারে. It is possible because if you set n is equal to that integer and m is equal to 0, 0 plus b will give you b.
B, yes.
Right? So it's possible to get any integer as a result for this function. Is that clear to everybody?
Yes, miss.
Yes, ma'am.
Okay, what if we change the function to m minus n? Will the outcome still be the same for m minus n?
No, miss.
Okay, by outcome we mean, do we have the same solution for 1 to 1 and onto for m minus n? First of all, let's answer the question whether the function is going to be one-to-one or not for m minus n. Is the function going to be one-to-one for m minus n if we change it to m minus n? Is it going to be one-to-one? Yes or no? What do you guys think?
Yes, I think it's going to be 1-to-1.
It's going to be one-to-one. Okay. Why do you think it's going to be one-to-one? Before that, what about the rest of you guys? What do you guys think? It's going to be one-to-one? Yes? No? Don't know? Sleeping?
I think it can be 1-to-1 if we can prove the contrapositive to be true. Like yeah, whatever. Yeah, that's it.
Okay. So everybody else agrees that it's going to be one-to-one, yeah? Okay. What is your reasoning? Why do you think it's going to be one-to-one?
Means because f01 and f10 is not going to be same.
So basically you're saying that the result is not going to be equivalent anymore. All right?
Yes, ma'am.
That is, since they are, we know for a fact that 0, 1 and 10, these two pairs are not equivalent. The
Yes.
problem was where? The problem was the hypothesis was true, but the conclusion wasn't. But this time the hypothesis isn't true anymore. That is what you're saying, right?
Yes, miss.
Okay, very good. Right, good. Correct there. However, the hypothesis isn't correct for this specific example. The universe of the set of all integers, is that comprised of only 0 and 1?
No, miss.
No, it's not. There are other integers there. Can you say that this thing, the hypothesis, is not going to be true anymore for all other integers? No, you cannot. Can any of you not think of any pairs where you get the result, you get the same result for m minus n, but the elements which give you the result are not equivalent? What about the ordered pair of 6,
and
3 and 9, 3? Those two pairs. The ordered pair 6, 3 and ordered pair 9, 3. Is 6, 3 and 9, 3 equivalent to each other, these two pairs? Are
No.
these two pairs equivalent to each other?
No.
No, but apply the function m minus n on this pair. Each of these pairs. What do you get in the result? For 6, 3 and 9, 3. Sorry, 9, 6. For 6, 3 and 9, 6.
3.
3.
3.
For 6, 3 and 9, 6, even though the ordered pairs are not equivalent to each other, the result, both of them give us 3. Okay?
Yes.
So just don't dwell straight into it and just go ahead and say that, okay, no, since you have changed the function, this is going to be one-to-one. You have to, don't restrict your vision to a specific example. Consider all possibilities. For example, in the previous case for R to R plus, we forgot 0. We forgot that boundary value 0. Remember, we have to consider all boundary values, all right? All possibilities. So don't restrict your vision. So yeah, this is still not going to be one-to-one for m minus n. For 0, 0 and 1, 1, these two pairs, 0, 0 and 1, 1. These two are two different pairs, right? 0, 0 and 1, 1. 0 plus 0 will give you 0. 0 minus 0. 0 minus 0 would give you 0. 1 minus 1 would still give you 0. Two different pairs giving you the same result. So another example. So this function is still not going to be one-to-one. Is that clear to everybody?
Yes, miss.
Yes, miss.
Now to
Yes,
answer the
ma'am.
question, is this going to be onto or not? What do you guys think? Is this going to be onto?
Miss, I think it will be on to.
Okay. What about the rest of you guys? Okay. So if any of you think that it is going to be onto, what is your reasoning for that? Let's go with the reasoning first. If you think that it is going to be onto, why do you think it's going to be onto? Okay.
If one reason can be we don't have any restriction on positive or negative integers. We have.
Yeah, think of it that way.
Yes,
But
miss.
see, if we follow the same approach that we followed here to show that the function for m plus n, the m plus n function is onto, if we followed a similar approach, something like that, for m minus n, if the function now is m minus n, here we still have the same domain and codomain, yeah?
Yes,
Now,
miss.
instead of setting m to 0, what if we set n to 0 instead of m? Instead of m, what if we set n to 0 and m to b?
B.
Yeah.
B. Yes, miss.
And what is b minus 0?
B.
B. There you go. Even there, whichever integer you want as the result, just set m equivalent to that integer and n equivalent to 0. And you will get that integer in the result. If that is possible, then it's onto. So you see, it is possible to get any integer in the result if you just set m to the result that you want and n to 0. So since that's possible, it's onto. Okay? Is that clear to everybody? Yeah, Fahim, go ahead.
Miss, I can also set n to be minus, like negative. Or is that going to be wrong?
You can set n to be negative. Okay.
0 minus
So,
b. 0
aren't you
comma minus.
restricted? Okay. Then, okay, 0 to minus. Okay, in that case, aren't you restricting n? Because n will be from the set of all integers. Yeah,
Yes,
all integers. Remember, in order for an expression to be a function, all elements of the domain must be mapped. Yeah?
Yes, miss.
And if m minus n, if that is your function, m minus n, and there, you say that n is always going to be negative b. Okay?
Yes, miss.
Yeah. So you can say that. In that case, yeah.
Okay, miss.
That means if we don't
However-
consider it to be 0, then what will happen?
Come again?
Yes, if we don't consider m to be 0, then what will happen?
If you don't consider n to be 0. So we're talking about possibilities, okay? So for example, what Fahim suggested, the reason we didn't go in that direction is because not to bring in the confusion regarding the domain, all right? However, if any of you went ahead and explained it in that way, that 0 minus b would give you what? 0 minus minus b, all right? It still gives you b, okay? So what is our ultimate goal for this function to be onto? To be able to get all positive integers. Whatever result we want in the integer, we will put the negative of that for the value of n. Okay, that is possible. All right, the reason we didn't head in that direction head first is because it's a set of all integers, so we want to consider all positive integers as well and all that. All right, so not to bring in that confusion, but is it possible to do something like that? Yes, it is. Okay, if n is equal to minus b, first of all, answer this question. If n is equal to minus b, whatever result you want here, okay, whichever integer you want in the result, the negative of that integer, is that in the domain, yes or no?
Yes,
Yes.
miss.
Yes, it's in the domain. So if it's in the domain, then it's something that we are allowed to do. So you could also say something like that. Yeah. So yeah, if you fix n to 0, in that case, you'd have to fix m to b. If you fixed m to 0, then you'd have to fix n to be to minus b. Okay. All right. So that is what we have to do. Arshad. If m is 0, then n has to be minus b. If n is 0, then m has to be b for m minus n. Does that answer your question?
Yes.
For this specific example, m minus n. Amader basically mean like you don't have to consider all of that. তোমার just যে কোনো একটা দেখালেই তো হলো, right? b, 0. A order রে যদি আমি রাখি, that is m is equal to b, n is equal to 0. In that case, we can get the result b, right? Our goal ultimately is to be able to get a result which is applicable for all integers, okay? Whichever way you do it. We want to show that it is possible to get any integer in the result, whichever way you do it. If you say that you'll do it by setting the inputs to be 0, that's fine. If you set it to 0 minus b, that's fine too. As long as you can show that in the result it's possible to get any integer, okay? Now, instead of setting the domain and the codomain to the set of all integers, what if we changed the codomain, for example, to the domain, for example. What if we change the domain to the set of all positive integers? That is z cross z এর জায়গায় যদি z plus cross z plus থাকতো, in that case.
মিস স্টিল এটা অন টু থাকতো, বাট আমাদের ওই যে মাইনাস দিয়ে প্রুফ করতে পারতাম না, আমাদের এই জিরো ইউজ করতে
Exactly, very good. Exactly. Still on to থাকতো, right? Now what if the domain changes to the set of all positive integers?
সেমই থাকতো, আই গেস।
I don't think so. 0, 9. So like there would be some integers that won't be mapped in the codomain. I think.
আচ্ছা, হ্যাঁ, জিরো বসাতে পারবো না।
Yeah.
Exactly. Okay, so if the domain is the set of all positive integers, in that case as well, think about that again, what you just said.
Yes, miss. I cannot use zero.
So yeah, this can be confusing. Just this is practice, right? This is practice for us, so that we bear in mind that when we solve the problems, we have to think about all possible values. First, jeta korba always boundary value gula consider korba. What are the boundary values? Examples are 0, a positive value, a negative value. All right. Ishob shop boundary we have to consider possibilities. Okay. And then in case of real number, fractional values. Okay. So all possibilities we have to consider. Okay. So is this example clear to everybody? Anybody here who's confused? Okay, good then. So in the exam, you should expect similar problems, all right? You'd be given a function and you'd be asked to determine whether the function is onto or one-to-one or bijective, all right? So yeah, we'll get into bijective functions just in a bit. So yeah, you should expect problems such as these, similar to this, or even more tricky, or even trickier, all right? So if you go over the problem set 2, there you'll find specific problems from the exercise of the book, and other problems as well if you want to solve other problems from the exercise. So from there you'll get enough practice, I hope, in order to find out, in order to be able to determine whether a function is onto or one-to-one or what, all right? So go over those examples. That will broaden your idea about how to find out whether a function is onto or one-to-one and all that through practice, all right? Go over those, and if you have any problem, obviously you can send me an email. Okay, now bijective functions. We call a function bijective. Yes, is there a question?
Before that, miss, like আগে শিখেছিলাম miss, there was one-to-one function and there was one-to-many function. So this on-to function is like same as one-to-many function, or is it different?
No, onto function, we are not going to term it as one-to-many function, all right?
Okay.
One-to-many means what? One-to-many means that one element, one specific element from the domain can be mapped to many elements from the codomain, which violates the definition of function itself, all right?
Okay.
So if we say that the relationship between student and course is what? One-to-many, you could say that.
Yes, miss.
A course can have many students. So this course, for example, has many students. So that is the relationship. However, is this a function? No, it's not. Okay, so that's a different thing.
Okay, miss.
Okay. All right. So a function, we call it bijective, or if we call it a bijection or a one-to-one correspondence, when that function is both one-to-one and onto. When it's both surjective and injective, we call it bijective. Okay. So why is it important to identify whether a function is bijective or not? Because bijective functions have inverse. Inverse functions exist for only bijective functions. Okay. Now, on that note, what is an inverse function then? For any function f which maps a to b, if this function is bijective, then it will also have an inverse. And its inverse will be denoted with f inverse 1 in this manner. F inverse 1 denotes the inverse of this function. Okay. So f inverse 1, the inverse actually maps the set B to the set A. The set B, which was originally the codomain, maps the set B to the set A, which was originally the domain in the function f. F inverse maps B to A, where every element of B, if you apply the inverse function, you get a unique element of A. Okay? That is f inverse B is equal to A. Basically, you have to be able to retrieve the image. Sorry, you have to be able to retrieve the pre-image from the image. Okay? Using the inverse function. Let's look at examples. So this is the pictorial representation of an inverse function. A normal function maps A to B by B is equal to FA. The inverse function goes the other way. Extracts the pre-image, maps B to A by F inverse B. Okay. Let's look at the example of the square function again. Let's say that we have a set A, which is the set of all non-negative real numbers. Remember, 0 is there in the set of all non-negative real numbers. Yeah. So let's say the square function maps the set of all non-negative real numbers to the set of all non-negative real numbers. That is for the domain and codomain. For both of them, we have the set of all non-negative real numbers. Okay. We have to find out whether the inverse exists or not. So in order to answer that question, whether the inverse exists or not, before that, we have to find out whether the function is bijective or not. Because if the function is not bijective, then the inverse does not exist. First question is what? Does the inverse exist? In order to answer this question, you have to find out whether this function is bijective or not. And in order to answer the question whether this function is bijective or not, you have to find out whether this function is both one-to-one and onto or not. Now, is this function one-to-one? Remember, the domain and codomain, both of them is the set of all non-negative real numbers. Is this function one-to-one?
Yes, miss.
It's non-negative, right? Non-negative. So no, x will never be negative. X will always be positive. X will never be negative. X will be always be positive or 0. So you will never get a scenario where you get the same result for two different x's, right? So this is, yes, this is one-to-one for this specific domain and codomain. This is one-to-one. Now to answer the question whether this is onto or not. Real numbers, see, non-negative real numbers. So fractions are allowed. We've already established that if it's real number, fractions are allowed, then it's possible to map every real number in this square function to another real number as the pre-image, all right?
Yes,
So, yeah.
Miss, I have a question.
Yeah, go ahead.
Miss, to the domain, I have a value, and after applying the function, I get the same value for the codomain. Is that still a one-to-one function? Like 1 square is 1.
Yeah, well, as long as no other different element from the domain has the same result, it's one-to-one. There's no problem with that.
Okay.
Okay, yeah. So onto or not, it is possible to get any real number in the result of the square function, right? Because it's real number. Fractions are allowed in both domain and codomain. So it is also an onto function, okay? So f is indeed bijective. And since it's bijective, it has an inverse function. What will be the inverse function? Now, the inverse function will be that function which, when applied to the result, returns the element, the original element of the domain which gave you that result. Or in other words, which returns the preimage to you from the image. Let's say y is the image. Okay, y is the image. That is y is the result you get after squaring. Okay, so if you apply the square root on y, what do you get? You get back the preimage. Okay, x, the preimage, the element on which you squared, you applied the original function to get to y, the image. Okay, so once you apply the square root, you can retrieve the preimage from the image. Okay, that is, you can revert back. So that is your inverse function. So f inverse y is equal to square root of y for all y present in A is your inverse function for this specific square function for the given domain and codomain. Is this clear to everybody, the example?
Yes, miss.
Yes, ma'am.
Cool. Okay, so let's look at another example. So let's consider the function x plus 1. Now, in order to answer whether this function is invertible or not, to answer that question, first of all, whether this function is invertible or not, what do we have to find out, guys?
Is it bijective or not?
Is it bijective or not? And in order to do that, we have to find out whether it's both surjective and injective or not. That is, whether it's both onto and one-to-one or not. Now, is this one-to-one? Yes, it is. Why is that? Because see, it's just an incremental function. That is, whatever input you give here, x, you just increment it by 1. And what is 1? 1 is a constant. 1 is a constant. So if you change the input here, the output will mirror that change as well, right? If you change the value of x, the output will change correspondingly for the domain and codomain of the set of integers. If you change the input, the output will mirror that change because 1 here is a constant. Nothing else will affect the output. If x has a different value, the output will have a different value as well. Okay? So in other words, think about the condition for a function to be one-to-one. What was that? These were the conditions. And the function that we have is fx equals to x plus 1. Now, if this is true, we have to show that this is true. If this is true, what do we have? Let's say we have an element x from the domain and another element y from the domain, x and y. These are the two elements from the domain, two different elements from the domain, x and y. So if the results of these two, the results of this function that you get from these two elements from the domain are equivalent, then what do we have? X plus 1 is equal to y plus 1, right, guys?
Yes, miss.
Now x plus 1 is equal to y plus 1. From there, what do you get? 1 on both sides will be cancelled out, right?
Yes, miss.
Since it's an equivalency. So in the result, you will get x equals 1. Sorry, x equals y. So you started from the assumption and you got to the conclusion. Okay, even if you go at it the other way, you'll get the same thing. X not equals to y. If you take two elements from the domain x and y, and if they're not equivalent to each other, x is not equivalent to y, then x plus 1 is not going to be equivalent to y plus 1 either. Just add 1 to both sides. That's allowed. So x plus 1 is not going to be equivalent to y plus 1 either. And obviously, it makes sense. This is a function where you just increment the input by 1. Okay? So, yes, this function is going to be one-to-one. Because whatever input you give here, if the input is changed, that is mirrored in the output. Okay? All right. But is this function going to be onto? Now let's answer that question. In order for this function to be onto, what do we have to show? We have to show that every element of the codomain can be mapped in this function. What is the codomain? The set of all integers. That is, it is possible to have any integer as the result of this function. Any integer as the result of this function. Okay? Is that possible now? For x, you have integer. X can be any integer. Can the result be any integer as well? What do you guys think?
Yes, miss.
Yes.
Yes, miss.
Yes, the result will be any integer as well. Why is that? Because x plus 1 is just a linear straight line, right? So if you have an integer here, you can have an integer here as well. All right, so since x can be any integer, the output can be any integer as well. Okay, so if you think about the entire set of integers, you can have any integer here as the result. Okay, what do you have to do? You have to pick a value of x which is just one lesser than the result that you want, right? Does it make sense?
Yes, miss.
Yes, ma'am.
So yeah, the function is onto. Let's say y is the result of this function. Let's say y is the image for x. Let's say y is the image of x. For any integer x, once you apply this function x plus 1, the result you get is y. That is y is from the codomain. So fx is equal to y, or in other words, you will get fx is equal to y if x plus 1 is equal to y. That is, the result is y, right? So y is equal to x plus 1. Okay? And now this will happen only and only if x is equal to y minus 1. X is an integer, y is an integer, so this is possible. Okay? X is equal to y minus 1. X can be represented as y minus 1, right? X is an integer, y is an integer. Both of them are integers. Whatever result you want here, just reduce one from that, and if you select that as your x, you'll get any possible integer as the result. Okay, so f is onto, and f is also 1 to 1. Is everybody clear with this, that f is both onto and 1 to 1? Before we move on, that basically f is a 1 to 1 correspondence, or that f is a bijection. Is everybody clear on that?
Yes, miss.
Yes, ma'am.
Okay,
Yes, ma'am.
now that we've established that, it means that f is invertible. So if it's invertible, let's find the inverse. What is the inverse? The inverse is that function which returns the pre-image to you from the image. The image that you have from that image, if you can get back the pre-image, that is your inverse function. We already should have a hint of what will be the inverse function of this function.
Y
When
minus
we-
1.
Exactly. So let's say y is some image of x. Okay, so y is an image of some x. Y is an image of some x. So y is equal to x plus 1 in that case. Then if y is the image, how can you extract the pre-image from the image in this equation? How?
Just making x the subject.
Exactly, by just doing that. If x is equal to y minus 1, that is, you put 1 on the other hand side, then you can retrieve x from the value of y. It means that y minus 1 is that element in the domain, y minus 1 is that element of the domain, that element x of the domain, which is mapped to y by f. Okay, so the inverse function will be f inverse y is equal to y minus 1, assuming that y is the image of x. Okay, so any questions so far?
Miss, I have some questions.
Yeah, go ahead.
Can you go to the previous slide?
Yeah, surely.
Miss, there says note that fx equals to y if and only if x plus 1 equals to y, which holds if and only if x equals to y minus 1. What does this mean?
Okay, so okay, if y for if y is the image, all right, if we say that y is the image, what does that mean basically? That is fx equal to y, that is the result you get for the function. Once applied to x, you get y for that, right?
Yes, miss.
What does that mean? It means that x plus 1 is equal to y, right?
Yes.
That is what it means. F of x is if and only if x plus 1 is equal to y, means that in order to get y in the result, x plus 1 is equal to y. And this will be true if x is equal to y minus 1. That is, in other words, if x plus 1 is equal to y is true, then x is equal to y minus 1 is also true. All right? That is what it means. As simple as that. That basically, if it's possible to get a y from x plus 1, it's also possible to get an x from y minus 1, because both of them are integers, right? So for
Yes,
any integer x, if you add 1 with it and get y, okay, then you can have any integer y as well. By deducting 1 from it, you can get back x, right? That is what it means, what we just discussed for onto.
Yes, miss. So this is basically the inverse.
Yes, y minus 1 is basically the inverse. The way we find the inverse is very simple, similar to how we showed that this function is onto. Yeah, the idea is very similar.
Yes, miss.
Basically in onto, and it makes sense, right? In onto, we want to map every single element of the codomain. And in finding the inverse, we want to find that function which returns the element of the codomain from the corresponding element of the domain. So the processes, it makes sense that they're going to be similar, all right? So the way we proved that this function is first of all bijective, and then we found out the inverse. Is everything clear on that ground?
Yes, miss.
Okay. You would have similar problems like this as well in your exams. You might have to find out whether a function is bijective or not, and then find the inverse from there. So for this as well, there are many practice problems in the problem set 2. So go over them, and some more I would recommend in order to get a good grasp on these methods. Okay. Compositions of functions. So for any function g and any function f, where g maps the set A to the set B, and f maps the set B to the set C, we, by composition of functions, by composition of these two functions, we mean something like FOG or GOF. Here, what it means, this specific expression FOG, this expression means that you first apply the function g, the one on the furthest right. That is the one that you first apply. The one on the furthest right, you apply that function first, and the result of this function, the result that you get by applying this function, on that result, you apply the function f, all right? The next one, going from right to left, okay? So FOG is equal to f of g of a. That's how we call it. So for any element a, you first apply the function g, and on that result, you apply the function f. Now, in the mapping, you will see that it is mapped from a to c. Why is that? Because we first applied the function g, right? It's FOG. In FOG, you first apply the function g. We first compute the function g. When you compute the result of the function g, you will see that it's mapped from a to b. A to b. So the first function you're computing in this composition, the domain of that function is a. So we start with a. And then it maps the elements of a to the elements of b. And then you apply the function f, which maps the function, which maps the element of b to the elements of c. So finally, you have the elements of a mapped to the elements of c. Okay. So FOG is equal to f of g of a mapped from a to c. A to c. Okay. G of f, however, in that case, GOF, instead of FOG, if you had GOF, in that case, instead of G, you would actually have to compute F first, because F is on the furthest right now. You'd have to compute F first and then go to G. Okay. Let's look at an example. For example, let's say F and G, both of these are mapped from Z to Z. Both of them have the same domains. So we don't have to worry about the mappings of the composition, all right? We don't have to worry too much about A to C or whatever, because both of them, as we can see, are mapped from Z to Z. So same domain and same codomain. So we don't have to worry too much about the domain and codomain of the composition. Okay. Now, in order to find the composition of F and G, the composition of F and G is FOG. The composition of F and G is FOG. So when you do that, first you compute which function, F or G, which one for FOG?
G.
G. So if you compute G first, in that case, you have to apply this function first, 3x plus 2. You get 3x plus 2. You have to apply this function on x first. So you have 3x plus 2 here, and the result that you have here, 3x plus 2. On this result, you apply the function f. So fx is equal to 2x plus 3. F of 3x plus 2 will be equal to what? Instead of x, you'll have 3x plus 2 here. So there you go. This is the result of FOG. In case of GOF, however, you compute the function f first. All right. And if you compute the function f first, the result of f is 2x plus 3. And you use that result to apply the function g, which leads you to a different result. So as you can see, even from this example, that FOG and GOF, they're not equivalent to each other. There might be a certain scenario where they could possibly be equivalent to each other, FOG and GOF. It could be possible, but it will not be the norm. All right. So it will not be the norm. FOG usually won't be equivalent to GOF. Okay. So this is how we pictorially represent the composition of functions. So if G maps A to B and F maps B to C, then F of G maps A to C. Okay, in this way, where F is equal to, sorry, here you will have F of G of A. Okay. Finally, the last topic of functions that we want to discuss: floor and ceiling functions. Okay, so if X represents any variable, if X is a variable, that represents any real number, the floor function applied on this real number converts the real number into the largest integer that is less than or equal to 6. Okay. So for any given real number, X is a variable that can take the value of any real number. The floor function applied on it gives you the largest integer that is less than or equal to X. Floor, right? So you go down. Less than, largest integer, first of all, largest integer that is less than or equal to X. Okay. And we denote it in this format: half of a third bracket or something like that, or half of a square brace, and the bottom part of it, basically. Now, the ceiling function is the opposite of floor function. So for a variable which can assume the value of any real number, the ceiling function this time actually converts this X to the smallest integer this time, the smallest integer that is greater than or equal to X. The smallest integer that is greater than or equal to X. Ceiling. So it goes up, okay? It goes up. Ceiling, so goes up. And as you can see here, that is mirrored in the symbol as well. This is the symbol we use. This is how we denote the ceiling function applied on the variable X. So if you have any random number, give me any random number that also has a fractional part. Give me a real number, guys. Give me a real number which is not a whole number. Any real number.
Two point
1.3.
Sorry?
1.3.
1.3. Cool. 1.3. So if X is equal to 1.3, then for the floor function, what we will do is we go down, right? The largest integer that is less than or equal to X. First of all, will it be equal to X? Will it be equal to 1.3? No, it won't be, because 1.3 is not an integer and we want an integer. So it won't be equal. So the next option is largest integer that is less than X, right? So
One.
floor function, so we go down. So the result, yes, you're correct. The result is going to be 1. The largest integer that is less than X, since it's not an X is not an integer itself. The ceiling function on the same function, however, on the same value, however, the ceiling function on the same value would give you what? 2. Ceiling, we go up, right? So it will give you 2. Let's do some more examples. So the floor function applied on 4.1 gives you 4. Because floor, we go down, right? Floor, so we go down. Okay, the largest integer that is less than or equal to this value. First of all, it will not be equivalent to this value because this is not an integer. So we have to go down. The largest integer that is less than this value is 4. So that is the result. This floor function applied on 5 is equivalent to 5. Why hasn't this changed? Can anybody tell me? Is this correct?
Yes.
Yes, it's correct.
Integer.
Means because 5 is also a real number.
5 is a real number, yes. All of these are real
And an
numbers, but
integer.
5 is an integer as well.
Yes,
5
yes.
is already an integer. 5 is already an integer, so you don't need to make any change at all. Negative 6.2 now. Why is it minus 7 instead of minus 6?
Yes, because minus 7 is smaller.
Yes, exactly. So be careful with negatives, all right? So since it's negative 6.2, the floor function would give you negative 7. The largest integer that is less than minus 6.2 is minus 7. Okay. So now for the ceiling function, however, you will see that for the ceiling function, it changes. 4.1 gives you 5, in fact, because we are going up this time, right? Ceiling, so up. Ceiling goes up. So 5. And this one remains the same, obviously. Negative 6.2 this time gives you negative 6. Again, because negative 6 is larger than negative 6.2. Some other examples, see, the floor function applied on half, which is 0.5, is 0. All right? Why is that? Because 0.5, the largest integer, that is less, that is less than 0.5. The largest integer that is less than 0.5 is 0. However, you apply the ceiling function on the same value. If you apply the ceiling function, you get 1. The smallest integer that is greater than 0.5. So remember, for floor, we go down. We had 0.5 here. For floor, we went down to 0. For ceiling, we went up. We had 0.5 here. We went up to 1. Here again, minus 0.5. We go down. So minus 1. Minus 0.5. For ceiling, we go up. So 0. Okay. And similarly, just others. So does anybody have any confusion with any of these examples of ceiling and floor function, or the definition of ceiling and floor function?
No, ma'am.
We did this kind of math, but we didn't know that it was ceiling or like floor functions.
Yeah, this is what it originates from. The idea of rounding up and down, it originates from the idea of ceiling function, floor function. Okay. So no questions, right? Okay, cool. Very good then. In that case, we are done with the topic of functions with this. So we'll have the quiz on Wednesday, right, guys? Remember? So with the quiz, we will be done with set theory. And then
Miss, how long